Hello, this is Mrs. Scarple, and this is our video for topic 1.9. In this video, I'm going to cover how we find the limits as a function approaches vertical asymptotes or as it approaches a hole. So for example, I have two graphs here, both of them with something happening at x equals 1. The graph on the left has a hole at x equals 1, so we just have one point that isn't going to be included. And the graph on the right has a vertical asymptote at x equals 1. So my graph will never intersect or touch that line. I want you to pay attention to how we write these limits. So we're not talking about end behavior as in what's happening when x increases or decreases without bound, meaning I'm continuously increasing the x on my number line or decreasing my x on my number line. And this time it's as I approach on the left side here a hole, or on the right side here a vertical asymptote. So that's why you see as x approaches 1. Now you'll also notice that we have superscripts next to these numbers. A 1 with a negative superscript means from the left. And a 1 with a positive in that superscript position means from the right. Now when we have a hole, that limit should be the same value as we come from left to right because it's a point that we're not including in the graph at that point. When it comes to a vertical asymptote, they may not be the same value, but what is going to be in common with the asymptotes is we're either going to have the function continue to increase or the function will continue to decrease as we approach the asymptote from left or right. So that's why you'll see the number with that sign again in the superscript position. The negative means from the left, and the positive on the superscript position means from the right. So I'm going to jump ahead to example 2 in your notes. And we're going to write right and left limit statements. And I'm going to do this with both exercise A and exercise B because we've got two different things happening here. For exercise A, x minus 2 is what I have in my denominator, but it doesn't appear as a factor in my numerator. So that tells me that I have a vertical asymptote here. When I have a vertical asymptote, if I think about the graph, that means I have this line that my function's not ever going to intersect or touch. And this particular vertical asymptote occurs at 2. So I'm going to do a sign chart, but I'm only going to look at it for as I approach 2 from the left and from the right. And because it's an asymptote, I want to use a decimal value that's really close. A decimal value that is really close to 2, but not exactly 2. And the reason I want to use a decimal value is because if I go to a whole integer, I could potentially be crossing or even intersecting my x-axis at that point. So that's why we want to be really close. So I'm going to test, and I'm just going to write the number here. I'm going to test what happens when I use 1.9 for x, and I'm going to test what happens when I use 2.1 for x. So again, sign chart, I'm plugging it into all of my factors, and I'm just looking at the sign. If I have 1.9 subtract 1, that's going to give me a positive value. If I have 1.9 plus 3, that's also going to give me a positive value. If I have 1.5 minus 2, or I mean 1.9 minus 2, that's actually going to give me a negative value. So on the left side of my asymptote, my graph is actually going to be below my x-axis, and it's going to be getting really close to that vertical asymptote. Let's try 2.1. 2.1 minus 1 is a positive number. 2.1 plus 3 is also a positive number. And 2.1 minus 2 is a positive number. So I have a positive divided by a positive, giving me a positive value, meaning to the right side of 2, my value of my function is constantly increasing. So let's write our limit statements. On the left side, we're going to have the limit as x approaches 2 from the left of f of x is going to equal, on the left side it shows a negative, is going to equal negative infinity. Then on the right side, I'm going to have the limit as x approaches 2 from the right of f of x. On the right side of 2, the function is increasing, so it's approaching positive infinity. For b, and the reason I'm only focusing on the 2 is because we're writing the statement as x approaches 2 for each of the following. So that's why I'm only going to focus on the 2 here, even though I do have a vertical asymptote at 3. We're only focused on what happens at x equals 2. Now x minus 2 is a factor in numerator and denominator. So that tells me I have a hole with this particular problem. Because it's a whole, as I come from the left and as I come from the right, it should be the same value. So I'm going to do some work here for my value, and it's the same work that I was doing in previous videos when I would find the x value of my whole, but then would substitute back in to find the y value. So I'm going to take 2, because we're approaching 2, and we want to know what the value would be at 2 if it existed. So we're actually checking for the limit as x approaches 2 of x plus 4 over x minus 3. So to do that, I do 2 plus 4 over 2 minus 3, and that is 6 over negative 1. So the y value of that whole is going to be negative 6. So now when I write it coming from the left, I'm going to write the limit as x approaches 2 from the left, so that's that minus in the superscript, of f of x equals negative 6. And from the right, that's going to be my limit as x approaches 2 from the right of f of x equals negative 6. So when you see that you're approaching an x value and you're getting the same, the exact same value, that's when you know just from looking at the limit statements that you also have a whole. When your limit statements, as you approach a specific x value from the left and right, when those end up going to some form of infinity, positive or negative, then you know you're going to have a vertical asymptote. And the reason I'm pointing that out is because I'm going to take a look at example A under number 3, and then I'm also going to do a graph under number 4 as a sketch. So I'm going to write an equation of a rational function with the following limit properties. So our first limit statements, you'll notice, are as x approaches 3 from the left, 3 from the right. They have the same value. So that tells me I have a whole at x equals 3. The two statements below, as I approach 1 from the left and 1 from the right, are approaching negative infinity and positive infinity. So that's telling me that I have a vertical asymptote when x is 1. So let's start writing this function. We're going to have f of x equals, for my whole, I know the factor has to occur in both numerator and denominator. That whole is occurring at 3, so I have to have x minus 3 in my numerator, and I need to have x minus 3 in my denominator. Then for my vertical asymptote, I'm going to need to have x minus 1. And because both of these are, or one is negative, one is positive, I don't have to worry about how am I going to make sure that they both end up negative or they both end up positive. So I don't need to do any work on that front, but I do need to make sure that my equation will allow me to have a y value of 5 when I find my whole. So I'm just going to include in this function for now a k value. And we need to find that value of k. To find that value of k, I'm going to set k over the only remaining factor, if I don't take a look at where my whole is at, is x minus 1. And that value, when I would plug in the 3, has to equal 5. So we know that we want k over 3, because that's the value of my whole, minus 1 to equal 5. That's going to be k over 2 equals 5. Multiply both sides by 2, and we end up with k equals 10. So I'm going to write this function fully now as 10 times x minus 3 over x minus 3 times x minus 1. So I have to find that k whenever I have this value for my y value for my whole. I need to do something like this to find k. I do, after taking a quick glance at example B, I do want to mention something here. Notice that both of these end up being positive. Because I need it to be positive on both sides, and because it is a vertical asymptote, and I always want it to be positive, I'm going to have to ensure that I have a negative, or I have something squared at some point. So my function, when I start writing this out, is going to be f of x equals, I'm just going to go ahead and write a k right off the bat, just so I get in the habit of looking for it. And let's use a different color that'll show up a little bit better for you on your screen. I'll go ahead and use red. So I'm going to have k. I know that I have a vertical asymptote at x equals negative 1, so that factor is actually x plus 1. And I know I have a whole at negative 2, so I'm going to have, oh, I forgot the 1 there. So I'm going to have x plus 2 and x plus 2 in my numerator and my denominator. Now, if I want this fraction to always be positive, even when I put a negative value in for x, I need it to be positive. So I'm going to square my x plus 1, because when I square a negative value, it will be positive. And then to find the k, I'm going to set k over x plus 1 squared needs to equal 4. To solve for k, we replace x with that negative 2 where the whole is located. So negative 2 plus 1 squared has to equal 4. So now we have k over negative 1 squared equals 4. Well, negative 1 squared is just going to be 1, so I have k over 1, or just k, equals 4. So we can write this function as 4 times x plus 2 over x plus 1 squared times x plus 2. And then I said I would do a sketch. Your sketches could look many different ways. We just have to make sure we have each of these properties. So I'm going to deal with the whole last, just because I want to see how the rest of my graph is going to look. So I'm going to give myself an XY axis, and we are approaching 4, so I don't really need much on the left side. So we are approaching 4 from the left and from the right. And we're told that the value of the function increases or decreases without bound at that vertical intercept. So we're approaching 4. Increases without bound on the left means that my graph is probably going to look something like this. Now, it doesn't necessarily mean it's going to be above the x-axis. It could come from below, but as we get closer to that vertical asymptote, it needs to be climbing. As we approach 4 from the right, we're going to be decreasing without bound. And since I made my left side look like there's going to be a horizontal asymptote, I'm making my right side look like it has the same horizontal asymptote. Now that hole, if I were doing this in pencil, I could just erase a little spot. So I'm not going to do any erasing right now, but when you're doing yours, just erase a little spot and then put a hole. Put an open circle there at 1 to indicate that there's a hole there. And this would be one possibility of that graph. So again, I would recommend if you're making a sketch, start with the vertical asymptote and how it's approaching that, and then place your hole to fit the rest of your graph. And this concludes our video on the limit statements as we approach the vertical asymptotes and the holes.